So this lecture is also on conservation of momentum. It's our last lecture on conservation of momentum. Last lecture, Friday, we just did a whole bunch of examples related to conservation of momentum, and that's what I'm going to do today as well. So the main formulas that we're working with are here. So this is the integral form of conservation of momentum. This is the time rate of change of our of the momentum of our control volume. So it's kind of an unsteady term. This is the net momentum flux into and out of our control volume. So in overall, the net momentum change should be equal to the sum of forces, as Newton's second law. It comes down to this very special form, very useful form that basically all these examples we've used this form of conservation of momentum. It's a lot more convenient than doing the integration. Today we're going to do two examples where we are going to do some of that integration because it's actually quite useful for the real world to be able to do that. So it's our last lecture on conservation momentum. Wednesday's lecture will be on Reynolds transport theorem, which is, kind of a generalized conservation law. And our learning objectives are just to analyze conservation momentum for control volumes with non-uniform outlets. So we'll see what that looks like, but just to motivate this. So this is a method that's actually used to measure drag in a wind tunnel. So what you do is, you remember I passed around that pitot tube? So pitot tubes are used to measure what? Velocity, right? So what people can do is actually create a big rake of pitot tubes and measure a velocity profile in a wake. So that's this picture in the top right shows what kind of that velocity profile looks like. So you can use conservation of momentum to determine, well, we lost all this momentum, so it has to have gone somewhere, and it gets transferred basically to the airfoil as the force of drag. The reason that we use this method to measure drag is that if we were to integrate the pressure, that's only one kind of source of drag. That's just going to give us the pressure drag. But overall, this method gives us the total drag on the airfoil. So you can see a couple of, so these are like manometers that are being hooked up to the pitot tubes in this rake. So those are going to measure the um, velocity through measuring the pressure. So the rake kind of placed in the wake of our object kind of looks something like this. So there's a ton of pitot tubes there. This is one example. This is another example that's probably better illustrated. So in this example, they have non-uniform kind of resolution. So you can see that each of these lines represents a pitot tube in their rake, and it's concentrated in sort of a part of the flow that changes quite quickly. So those are both for airfoils. Here's one where people used a pitot tube rake, wake rake, they're called, to measure the drag on a bird's wing. So the top left here kind of shows the cross section of a bird's wing, with that black box being where they inserted the pitot tubes. You can see you get a similar kind of velocity deficit in the wake behind a bird's wing. And here's another schematic of what this looks like. So we're going to learn today how to integrate this, assuming kind of really simple functional forms. So we're going to assume kind of a linear velocity profile that just kind of does that. But in the real world, this is used using numerical integration to integrate basically this profile to determine the amount of momentum that's been lost. So we're going to see how to do that today. Any questions on these examples I just talked about? No? Okay. So yeah, I'm going to do two sort of long examples today. So this first example is fluid is extracted from a pipe via a porous wall. So assume we know V1, V wall, P1, rho, and D. I'll show you what those are in a second. The question is to determine V2 and P2. The question also says to neglect wall friction. So normally we don't neglect wall friction in a pipe. We would do like major minor losses, which are frictional losses. But in this example, we're going to do that because it really simplifies the analysis. So what this looks like is we have this pipe here. So flow is coming in on this pipe, and then we have kind of a porous section of the pipe. The flow can leave out of. So I'll give you some relevant dimensions. So this pipe has diameter D. Flow in is at V1 and P1. Flow out is at V2 and P2. So the length of this porous section is 5 diameters. Okay, so the porous section, we actually know the velocity profile through this porous section. It's going to be a linear velocity profile that starts at some velocity VW right at the start of this porous section. By the end of the porous section, the velocity goes to 0. So we have a linear velocity profile. Give our coordinates. Actually, I'm going to do our coordinates in a second. Okay. So it's kind of contrived in that, we have this nice linear velocity profile along that porous section, but it allows us to basically do an example of conservation of mass and momentum with non-uniform outlets. So if the outlet was uniform flow, we could do basically just m dot v for our conservation of momentum, but it's not. So the steps in this problem, first step is use conservation of mass to determine V2. Second one is conservation of momentum to determine P2. So that's what the question asked us to do, is determine V2 and P2. This is a very typical, again, basically the steps I've followed for all the conservation of momentum problems. It's because our pressures don't appear in our conservation of mass. So just like pressure doesn't appear in the continuity equation, pressure doesn't affect our conservation of mass. That's just the velocities. So we have a relatively easy job to determine the mass flow rates out of 1 and 2. So m dot 1 will just be rho v a1, or rho v1 a1, which we know both of those. M dot 2 is just going to be rho v2 a2, which we know. So that's kind of our normal pipe inlet. The issue is we don't know the mass flow rate out of the porous section. Are there any questions about the problem setup before I get into more detail? Okay, so I'm going to, because this is kind of hard for me to draw, I made this model to show basically what our integral is going to do. So feel free to kind of sketch this integration that we're going to do, or I guess you can just look at the notes after. Okay, I guess that's stuck there. Okay, so here, how about this? I'm having issues with that, so I'll just draw it directly on the figure when you get there. Give me a second. I'm just going to restart my OneNote there. Okay, that's looking much better. Okay, perfect. So we're going to define a cylindrical coordinate system for this. So our cylindrical coordinate system, this is the start of our porous section. So that we're looking at the porous section. And I've drawn our velocity profile here as this linear velocity profile that starts at VW and goes down to 0. So our cylindrical coordinate system for this integration is going to have x equals 0 at the start of our porous section. So it will be x along the pipe in some coordinate r in the radial direction. And then the theta will be in the angular direction. So that's just a normal cylindrical coordinate system. Maybe I'll draw this a little bit bigger. It's kind of hard to see. So that angle is theta. And the velocity again is VW here and a 0 here. Okay. So our integral definition of the mass flux, if you look back at your notes, it's this here. So it's the area integral of rho v dot n hat dA. Okay, so our velocity, so we don't have a planar inlet, right? This is a cylinder that's losing kind of flow in all directions. So I've just drawn one kind of slice of the profile, but this profile applies over the entire, right? It applies over the entire cylinder. So this thing is losing fluid in all directions like that. So that's nice from the perspective of our v dot n part. So the v dot n is always going to be positive, and it's always going to be equal to that kind of local velocity. So we don't have v dot n is always, no matter where we look at our small area element, that velocity is just going to be kind of pointing straight outwards, always. So this integration, the other thing we have to look at is our dA. So I've drawn a small area element here. So our dA, again, like you might remember kind of from calculus, you assume like a small rectangular element. So this small element is going to have, I guess, two sides that we need to compute. So I'll give you, say this is dA here. So the length of this side is dx. Does anyone have an idea about the length of this side here? Remember, this is on a curved surface. So it's a arc length, right? Yeah, it's like a angle times radius, right? So that is going to be big R d theta. So where big R is kind of the maximum radius here. So we're integrating along the surface of our control volume. So we're not integrating over R, our radial coordinate. We're fixing our radial coordinate at big R, and we're integrating around the outside of our CV. So that's the area that we're doing. So we get dA is r d theta dx.
Applying our pipe is like we're ignoring the porosity. We're assuming it's non-existent in this area. That's what this is implying.
Well, it's kind of like we're taking, it is porous, but that porosity is, say, so fine that it's creating this linear profile, or maybe the porosity is designed to get this linear profile.
No, like what I mean is we're defining this area here, the dA.
Mm.
That's the area that fluid's exiting through, right?
Yeah. So we've, yep.
Based on that, and how wouldn't that mean we're technically integrating the entire surface area of this cylinder, which would imply that there's no cylinder?
I get what you're saying. So say the porosity is created by a bunch of small holes and stuff in this. So how do we know what to integrate over? The actual local velocity field is not what we're integrating here. We've kind of assumed like this resulting velocity outlet here with that VW down to 0. So we're not integrating like the small jets coming out of each hole. So we've treated like the velocity profile as a big kind of linear distribution. So we're just going to assume this is the type of modeling that's often done in porous media, where you kind of assume it's just like a porous face that has a certain area and a certain flow rate that comes out. That's kind of the net effect of the porosity. Any other questions? Okay. So I'll set up our double integral here now. Okay. So we're going to integrate over two different axes here. So we're integrating over the first axis we want to integrate over is along our circumference. So we need to integrate along theta. That's what changes along that axis. We also want to integrate along the length of the pipe. So we're going to do a bunch of integrals along theta and along x. So this double integral is going to be the x will go from 0 to 5d, where again the length of this is 5d in the x direction. Now theta will go from 0 to 2 pi of r. So that would be rho v r d theta. I'm actually going to draw these in color just so it's a little bit clear. So if you remember from doing double integrals before, the bounds correspond to like our two d terms. So in theta, we're integrating from 0 to 2 pi. And then in x, we're integrating from 0 to 5d. We're integrating a function here, v. So v is going to be a function. We can pull out rho and r here because they're constant with respect to both x and theta. So we have rho r integral of 0 to 5d, integral 0 to 2 pi. Okay, so I'll give you this linear velocity profile, but in general, this is something you'll need to come up with when you solve this problem. So our linear velocity profile is going to be VW 1 minus x over 5d d theta dx. So this here is just this function. Which is the linear velocity profile we were given in the problem. So v, this bottom axis is x. Okay, any questions on where I came up with that? So this is just the velocity, and our velocity is axisymmetric, so it doesn't change along theta. It only changes along x. Okay, so this integration then so remember, our velocity profile is constant with respect to theta, so we don't have to integrate anything with respect to theta. We can just pull that 2 pi out. So that integral 0 to 2 pi of d theta, that doesn't involve, the velocity isn't a function of theta, so that just becomes 2 pi integral 0 to 5d. VW is also a constant, so that can come out. 1 minus x over 5d dx. Okay, any questions? Yeah, so this integral is pretty straightforward. It's 2 pi r rho VW x minus x squared over 10d between 0 and 5d. And that gives us 2.5 pi d squared rho VW. So I've also used the fact that r is d over 2 here. So this is the mass flow rate out of our non-uniform. So that's just basically the integration of this linear function. Yep. We're going to give V2 eventually. We're basically, in order to do the mass balance for this whole thing, we know the mass in really easily. We know the mass out of the pipe really easily. We're just getting the mass that's leaking out now. So now we'll put this all together in a big mass balance to. No, no. In general, for the double integrals, unless you're in a math class, don't tell any of the math people that I said that the order doesn't matter. But you can flip the order of this integral. So yeah. Any other questions? Good. So I don't want you to worry that you're going to have to do a full-blown double integral, because that's not going to be the case. It's either going to be really nice and axisymmetric like this, where you don't have to integrate along one of the axes, or in the next question, you'll see it's kind of uniform along one of the axes. So you're just doing a 1D integral, not a 2D integral. Okay, so now we're going to do our mass balance. So we're going to do our mass is, okay, so we have mass coming in like that. So that's 1. We have mass leaving here. That's 2. The mass that we've just found, this m dot p, that's the mass leaving from this entire porous section. So it's the leakage out of this entire area. So that's quite hard to draw, but it's just kind of the mass leaving like our CV this way. So that's the term we found. So this is m dot 2 plus 2.5 rho d squared VW minus m dot 1 equals 0. So we can write this all in terms of velocities and diameters and everything. So the diameter is the same at 1 and 2. If we go back to the problem, the diameter is the same at 1 and 2. So we don't have two different diameters to account for there. We'll notice that a lot of this stuff is going to cancel. So our rows will cancel. I's are going to cancel. Diameters will cancel. So we're going to get V2 is V1 minus 10 V1. So just by mass balance with an assumed linear velocity profile, we can determine V2 in terms of, so basically that means if there was no porous section in this pipe, V2 would be equal to V1 just by mass conservation, right? So we're losing 10 VW to leakage out of this porous section. Any questions about this mass balance? Because this is the masses, and then we're going to do the momentum now. Oh, okay. So our again, yeah, VW is the, in case you forgot, VW is given in the problem. It's this starting velocity at the pipe, and then the velocity tapers down to 0 there. Okay, conservation of momentum now. So in the general form for the integration kind of form is V rho V dot n hat dA, sum of forces. By the way, I have assumed that this is a steady state problem. So make sure you write assume steady state. Okay, make sure you put that. So when this is steady state, we just have our integral term. That means that the net flux of momentum is equal directly to the sum of forces. Luckily, for this problem, our x direction doesn't only has these uniform inlets and outlets. So for our momentum, so that's going to be. Oh yeah, sorry. Is there a question? Yeah, you could definitely have tangential velocity. In this question, we've assumed straight normal velocity. So in that case, you need to account for that as the mass, do the mass balance as well. Let me think about how you do that. So your mass, yeah, I think you would just do the same integration, but your mass balance, like your mass balance in that direction, you wouldn't have all of the velocity turn into v dot n. Some of the velocity would turn into like a tangential component. But in this, that's why this question is nice, because it's all straight normal. Any other questions? Yep. Yep. Right. Yep. Yep. This this 2 pi r, this 2r turned into d. Yeah, so this is d now. Thanks for pointing that out. Okay. So our conservation momentum in the x direction is going to be quite nice because we don't have to do this integration in the x direction. So we only have in the x direction only average inlets and outlets. Okay. So we don't have basically the momentum flux in that through that porous section is going to be in our y direction. So there's no momentum flux there in the x direction. So we just have our nice formulas. P1, A1 minus P2, A2. It's actually quite nice. Okay, so I want to get to the second question today. So this is just basically algebra from here. We get using m dot is rho VA for each of those sections. We get this expression. Okay, so that's our pressure 2 as a function of our pressure 1 minus basically the momentum flux. Sorry, it's not the momentum flux in our y direction. It's we have to account for that we've lost some kind of mass flux out of that second exit. So we've lost some momentum there. So in this case, we didn't have to do integration in our x direction to find P2. So P2 is only going to act in our x direction, right? P2 is only going to be, again, P2 is normal. The pressures are always normal to our control volume. So the pressure created by this VW will act like this. So it will be kind of a y, or in this case, r direction balance. So any questions there? Okay. We're going to do a second example now. I can wait till it's caught up. So the second example is one of your homework problems this week, but I'm going to do it here just to walk in a little bit more detail of what's happening. So I might be going a little bit fast through this next one, just in terms of timing, but you have it in your homework, and the solution will also be posted. So we're going to do basically that example of a airfoil or some sort of body here that's being measured in the wind tunnel. So we have a uniform inflow. So we have a uniform velocity profile coming into this object. And then our velocity profile after the object will be, we're going to assume a linear velocity profile. So our linear velocity profile, it's going to be linear, and then it will go back out to this uniform, because away from the object we shouldn't expect any disturbance, right? So the distance of our linear section is going to be L over, sorry, this is going to be L. The length of our object is going to be L as well. Okay, and the velocity out here is going to be called u0, and it's not really to scale because this line is clearly longer than this line, but that also goes to u0. The other thing is we get our, let me just check. I believe this is u0 over 2 here. So it goes down to u0 over 2. Yeah. u0 over 2. Okay. So we're assuming this linear velocity profile because we're going to have to integrate this, and that makes it quite nice to integrate. So the steps for this problem will be a little bit different. So what the solution procedure for this is, we assume there's kind of a streamline that passes through here and this streamline ends up crossing exactly the point where we go back to u0. Same thing here. You start a streamline out in the free stream in front of this object, and there's a certain streamline that passes through this point. So after that point, there's no more momentum transfer or anything. The streamlines end up at the same kind of speed, so they're not slowed down at all. The problem is that we don't actually know this h here, so that we don't actually know like how far ahead of this object we don't know that height. So since we've defined a streamline, we have to use conservation of mass basically around this CV that looks like this. To determine h in terms of L, and then we have to use conservation of momentum to get so the problem is determine the drag force, or sorry, determine the drag coefficient. Of this object. So width into page. Okay. So any questions on the problem setup or the solution procedure? The streamline thing is not something you'll have to come up with, so it'll look like this for any problem that you do. It's sort of a streamline that we picture in our heads. We need to find out how far, basically how big that h is in terms of mass conservation. Okay. So we want to get h, and we do conservation a momentum. So our conservation of mass is this integration here. So V1A1 okay, so this, I'm going to pause. This is going to be a major source of error for you guys. So this V dot N at the inlet of our CV is negative, right? So our normal vector is this, normal vector points out of our CV and our flow points in. So that's where that minus sign comes from here. At the outlet, it's positive. So our uniform depth into the page is going to make this much easier to integrate. So B is the width into the page, and we're assuming this is kind of a constant profile into the page. I'll also show you what these. So this is our CV. It looks something like this. I'm sorry. So Y1 is okay. Y1 is like this. Y2 is like this. So A1 is this, the whole area of this front face, and A2 is the area of this back face. The other thing I'm going to just change is I'm going to say that this total length is 2h, and it will be clear why I do that in a second. So since this is kind of a symmetric velocity profile, we can just do half of it. So that will be negative 2 rho v1 is u0, and it's constant along that. So integral 0 to h dy1 is 2 rho integral 0 to L u0 over 2 1 plus y over L dy equals 0. Okay, so we have a constant velocity along 1. So it just is going to turn into basically velocity times length. Velocity times area, the mass flow right there. This integration comes from a linear function I've created here that goes from u0 over 2 to u0. I'm going to skip the details of this and just tell you it's negative rho u0 h plus rho u0 over 2 L plus rho u0 over 4 L equals 0. So h equals 3 over 4 L. Okay. This is I'm gonna make this a little bit neater just to explain what's happening in this integration. So I'm doing a coordinate at the face there defined as y1. So that's this y1. And I'm integrating from 0 to h. Remember I changed around how I defined h. So the total height is 2h. On the back face, I'm doing an integral with a coordinate y2. I'm integrating this linear function, which goes from u0 to here it's u0 over 2. And that integration goes from 0 to L based on the problem geometry. Okay, so any questions about that integration? Okay, so we actually know h now in terms of L. So h, like I drew, is a little bit smaller, and then it gets kind of pushed out. So h is 3/4 this height. So this height is 3/4 of this height. Okay. So now we're going to do conservation of momentum. Remember, the integral form of that is rho v dot n. So forces. The other thing I'm going to do here that I maybe didn't emphasize enough is I did 2 times this integral for the total mass flow rate through this face. So that's where this 2 comes from, and then I go 0 to h. Same thing on the back side. I do 2, 0 to L. So I'm going to do the same thing on the momentum side. You can do this because it's a symmetric inlet and outlet. It's symmetric about that center line. Okay, so this is negative 2b integral 0 to h. So rho, this front face, if this looks confusing, once you work through this problem, you're going to see that it's not actually that bad. The one thing you will probably get tripped up by though is again the signs of things like this. So that's why I'm writing these in red. So we're going to do the x direction here. So the velocity in the x direction at face 1 is u0. And that v dot n is going to be negative u0. Again, we're doing dy1. Okay, so the velocity at the back face is the u0 over 2, 1 plus y over L. So that's the first v. The v dot n there is positive because our normal vector is in the same direction as the velocity. So it's basically going to end up being squared, but there's sometimes a negative that kind of creeps in there that you have to watch out for. Equals negative f drag. So any questions here? Because it's equal to 0 on the right-hand side. So on conservation of mass, it's equal to 0 here. So the b, sorry, yeah, maybe I don't have a 0 in this line. So the b is, yeah, we can just pull the b out. Same thing with the rho. Like you'll notice, because we have uniform density, this doesn't actually depend on the density, the final answer. Any other questions? So you're right, it's not going to go away. And intuitively, we don't expect it to go away. So the drag force, if you have a longer wing, you should have a higher drag force. Yep. Yeah. So the blues in this line match. So this is going to be a major source of error. Okay. So these integrals are like a lot of this is going to be end up being constant. So this first integral, all of this stuff is constant with respect to y. Second one is basically the first integral squared. Okay, let me give you, okay, I'll give you the setup and then we'll skip to the result. 2b rho u0 squared h is 2 rho b u0 squared over 4. Okay, so that's the actual integration that you have to do. So really not too bad. If you expand it and then integrate it, it makes it easier. So we get f drag is 1/3 b rho u0 squared L. Just kind of all these terms have b rho u0 squared and everything in like that in them. So this will all combine into this nice form. And our drag coefficient is F drag for 1/2 rho U0 squared A, where A is LB, so that's the plan form area. It'll be told in a question like this on a test how you're supposed to know that. But A is basically the top-down area of whatever the shape this thing is. So that's 1/3 B rho U0 squared L for 1/2 rho U0 squared BL. We expect the drag coefficient to not have any dimensions, right? So everything should basically cancel and we should get a number. We get 2/3. So the answer for this question is just CD equals 2/3. So this CD equals 2/3 means that if you have some object and you put it, doesn't matter what this object is, you put it in the wind tunnel and you get a nice linear velocity profile underneath it. So you have some velocity hitting it, U0, and your linear profile after starts at U0/2 and then goes back up to U0. The drag coefficient is just 2/3 of that object. So none of the actual problem variables ended up mattering in this. It's just a non-dimensional drag coefficient of 2/3. So any questions? So for your tutorial this week, there'll be a problem like this, and then there'll also probably be like a problem with uniform inlets and outlets. Okay, there's no questions. That's everything for today. So thanks, everyone.